Hi everyone, the following is a video tutorial for the Incline Plane Simple Machines Lab with Onshape. First step, as always, is to make sure that you sign in to the Glenbrook South Enterprise. Once logged in, navigate over to the Documents tab. And then just like we've been doing, in your Teams folder for your specific class, you'll find a project folder called Incline Plane Simple Machines Lab. You want to open that project folder. And in there, you'll find the start file for this lab. So right click on it, say copy workspace, take out the Word copy and the dash on the back end, and then please write your first and last name up here at the front, space and a dash, and then leave the rest of the lab title as is. Once you click OK, it'll take a moment or two to populate. With this particular lab, what we're going to do, I can show you here on my second tab, is attach a wheel to this little C channel plate here. And you can see the number of constraints is actually a lot lower than what we've been doing in our previous labs. We only need 7 constraints to make this entire thing animate and work out. But we are going to try some new types of constraints while completing this lab. So we're going to look at a slider constraint. And then, of course, because we have a rotating axle, we'll have this revolute constraint. And those two together can be used to create what they call a rack and pinion relation. So up here along our menu bar, we have this gear relation. Here's rack and pinion. There's a screw relation and even a linear relation one. Well, we're going to do a rack and pinion. And what that means is as we travel up the ramp a certain linear distance, we want this wheel to also rotate. So as we're going up the ramp, we're moving a linear distance, the wheel is rotating, and there's a specific value that we'll have to input there to make this all look realistic. So you can see that number is showing right now on the screen, 12.56, which is actually the circumference of this wheel. This wheel is a 4-inch diameter, and the formula for circumference is diameter times pi. And so when you plug that into your calculator, it spits out 12.56 and some change. So I just put on there 12.56, and it actually makes a really nice animation. To animate this, we're going to drive it off of the slider constraint. Let me right click and show you here. For this, put it to 11 inches, and then I'll just slow it down a bit, bring it down to 150 steps. But you'll see then, as it moves that linear distance up the ramp, that wheel is rotating and actually looks very realistic. So that's the direction that we're going in for this particular lab. Something like this could be scaled up in the future with, instead of just one C channel here, an entire assembly of metal structure parts forming like a bigger robot design. And then you could have 4 wheels out there that are all rotating as you're moving around within this virtual space. So let's take a look. Let me go back here. We have our start file for the lab all loaded up now. And at the bottom, there are, again, 2 different tabs that you want to interact with during this lab. You have the assembly here for the incline plane parts. I have the wheel, the axle, the C channel, the bearing flat. And then I also have our effort and resistance forces on there. We'll include those as well. And one thing I left as a part of the start file was the second plate here. And I actually made that second plate by doing a circular pattern off the bottom one. And if I just open that up real quick, you can see the value for that is 10 degrees, which we'll come back to that number towards the end when we attach our resistance arrow. And we can offset it by 10 degrees as well there so that it looks like it's going straight down as you would normally draw that free body diagram. So let me just cancel out of that. 10 degrees, we're going to come back to that number. And to get started, I'm actually going to place this metal C channel first with the slider constraint. So slider is the 3rd one in here, slider mate. And I don't know why the wheel is jumping over here. It has nothing to do with the wheel. I noticed that when I was doing my test run for this lab video, but you can just ignore that for now. What we want to do is on the edge of the C channel here, I'm going to grab this inside edge right here and then move on down to the bottom of this inclined plane. And there's 5 holes going across here. I'm going to select this middle one. I actually want this inside wall, and I'm going to grab the very top middle point for that inside wall right there. So you can see those pieces are kind of glitching through each other. So we're going to have to do an offset. And the values for this are going to be -1 inch, which moves it out to the side. And then let's see, -2 inches to get up above. Let's see if that's moving in the right direction. Perfect. So -1 inch in the X direction, -2 inches in the Y direction. And the reason I'm using 2 is because, again, this is a 4-inch diameter wheel. And if I center these parts nicely based off of that dimension, the bottom of the wheel as it rotates will be just on the edge of this metal plate. So -1, -2. Check mark to finish that. And again, the wheel, I don't know why it moved like that, but you can just push it back outside of your assembly space for now. The next thing that I'll attach here will be my bearing flat. And it really doesn't matter if you put it on the inside or the outside. In my finished example here, I actually have it on the outside of the C channel. But in reality, if I was building this in real life, I probably would put it on the inside. So I'm going to put it on the inside now during this demo video. Grab a fastened mate. Again, you saw the wheel bounce there. I don't know why it's doing that. Grab the center point for the center hole for this one. And then we have 3 holes here to pick from. I'm going to zoom in and grab that middle one as well, just like that. And it's on the opposite side from where I would like it to be. So I'll just hit my flip arrow. Now that places it on the inside of that metal C channel. Green check marks to finish. Next, I'm going to bring in this axle, and I'm going to use the revolute constraint for that because we want the axle to rotate. So revolute. I'll grab this end point here on the axle shaft, and then over here, I'll grab the outside center point for the middle hole. Check mark to finish. No offsets for this one because we want that shaft to stick out far enough so I can attach the wheel next. So that looks good. And then the next constraint will be fastened as well between the wheel and the axle itself. I did have a little trouble making sure I got the center point on this one. So you might just have to play around a little bit as you're rotating to find that center point. I did alternately grab it based on one of these outer rings here. So you can see I have the outer ring highlighted, but then that center point right in the middle of the hole is what's showing. So I'm going to click there to grab that center point. And then on my axle, just rotate so I can get this edge, center point right here as well. And it actually went all the way into the wheel just like I wanted it to, so that's perfect. No offsetting or flipping here. If your wheel ended up on the outside, just flip it so that it's not, kind of virtually hanging off the edge of the shaft, and that should be good. Let me hit the check mark here. The green tire part will come with it. And now you can see if you switch to a right side view, that wheel is perfectly placed right on the edge of that metal plate here, which is exactly what you want. That's all because we offset this metal C channel 2 inches above the plate itself. All right, so just a couple more things to add here. We have our force indicators. I'm going to do a fastened mate off of the pointed tip here for our effort force. Make sure I grab that. There we go. Took a few clicks. And then on the C channel, normally if we were applying some type of force to this from the back end, we'd be applying it to the body of the assembly that we're moving. So I'm going to grab right here that same point that I used originally to mate the C channel and the metal plate underneath it. So this middle inside edge doesn't really matter. Just wanted to attach the green arrow to there. And then the last one will be our resistance force. So I'll grab the pointed edge for that. And then again, this wheel keeps kind of glitching and moving around as you're in the middle of constraining other pieces, but it does come right back. So don't get hung up on that. You should be fine to keep driving forward. There is a nice centroid point that you can click on right in the center here. So I'll just click on that. And then hit the green check mark for a moment. You can see the wheel comes back. Everything's fine. But if I go to my right side view, you can see that resistance arrow is on the angle here, that 10-degree angle, right? And so in reality, that force would actually be occurring straight down. So what we can do is rotate that resistance force just to be more perpendicular to the ground. So on fastened mate number 4, go to offset. We don't want distance. We want rotate around the X, down here, degrees, sorry, 10 degrees. That went further away from what I want, so I'm just going to switch that over to a -10, rotate it back up, perfect, green check mark. And now you can see if I go to my right-hand side, that resistance force arrow is nice and perpendicular to the ground here. All right, so that's pretty much it. This was a short one, getting everything assembled and in place. Now we get to see the magic happen a little bit. We do have to add our rack and pinion relation here. So let's go ahead and do that. That'll be the last step, rack and pinion relation. In order to do this, you have to select the slider and then the revolute constraint. So I'll grab slider and then revolute. And then I had mentioned this towards the beginning of the video, the distance per revolution. That's completely based on the circumference of this size wheel. So again, it was a 4-inch diameter. 4 times pi is 12.56. That's the number you want to type in here for the relation. Check mark. Now I can go ahead and animate this based off the slider constraint. And I'm going to drive it 11 inches up the ramp. It's a 12-inch ramp, 11 is fine for the animation here. I'm going to make it 150 steps, and I can leave it as reciprocate and have it go up and down. When I play this, I noticed this earlier when I did my test run, it just wants -11 then. So you can switch that over to -11 and play that out one more time. Now notice this, as it's moving up the ramp, the wheel is actually rotating in the wrong direction. So we can go back and change that based off of our rack and pinion here. So if I double click rack and pinion, you'll see there is one option here for reversing the direction. Let me hit that checkbox, and then we'll go try this one more time to animate 11 inches, -11, 150 steps. Play it. So now that wheel rotates perfectly as it makes its way up the ramp. And again, that relation value that we put in makes it seem very realistic. So this would be the finished assembly. Make this a part of the Screencastify recording that you make for the completion of this lab. Talk us through the process, talk us through the constraints that you added. If you want to add on to this assembly, by all means, add on to it, have some fun with it. If you finish early, you can always go back and add some more pieces to this, which I would love to see. And then once you have this working and you get that included on your recording, there are a couple of questions here on the drawing sheet tab. So if we switch over to drawing sheet, I have 3 views of the completed assembly on this drawing sheet, which actually I'm referencing these views from a separate file. So this is my completed version that I kind of used to plan out this lab. And that's one nice feature about Onshape is that you can place views of parts and assemblies from completely separate documents, which I think is really nice. So here we have the right side view of the incline plane here assembly, and I've included a few dimensions for you. So I did include that 4-inch diameter for the wheel as a reminder. For the linear distance across the bottom, we have 12.5. And for the height of this inclined plane, we're going to use a value of 2.22. So the first question I ask is, what is the slope length for that inclined plane? Remember to use Pythagorean theorem. So using 2.22 and 12.5, calculate what the length of the incline is. And then using that length value, what is the ideal mechanical advantage for the inclined plane? So if you remember, the formula is slope over height. So first use the height and the perpendicular distance here across the bottom to calculate the slope length, and then using the slope length divided by the height get you your answer for IMA. And as a reminder, you can input those answers here using the text feature, place a note right underneath the question, type in your response, and then please include this as a part of your recording when you make your video submission. So that's all for now. Thanks for joining me. Hope you enjoyed it. See you next time.